Welcome back again. I think in the last lecture we were talking about the kernel of a ring homomorphism. So kernel is the parallel concept as we have seen in the theory of group. So when we talk about group homomorphism, then there we have defined kernel. So here a similar concept, kernel of a ring homomorphism is there. So if you take let f from a ring R1 to another ring R2 is a homomorphism, then kernel of f is essentially the collection of all those elements of R1 such that fx equals to 0. And this 0 belongs to R2. Last lecture, we were discussing that this kernel is going to be a two-sided ideal. Okay, and I also asked you that whether or not this is a subring. Okay? This is a subring of R1. So, do you have any answer to this? Is kernel of F is a subring of R1? Have you verified it? Okay. So if f from R1 to R2 is a ring homomorphism, then kernel of f is a two-sided ideal of R1, and this we have seen in the last lecture. Okay. Now another result we are going to discuss is that about the this tells about when a map, that is a homomorphism, is 1-1. Okay, when a homomorphism is 1-1, and what is the condition should be what condition or what kind of elements should have kernel of f should have in order to f to be 1-1. Okay, so when we have some map, it is natural to talk about whether that map is 1-1 or onto. Okay, this is a natural question. But once we are talking about this 1-1 or onto, okay, so in a ring homomorphism or a group homomorphism, we have we get certain properties if it is 1-1 or if it is onto, something like this. Okay, so this theorem says that if f from R1 to R2, that is from a ring R1 to R2, is a ring homomorphism, then kernel of f is equals to identically 0 if and only if f is 1-1. F is 1-1. Okay, so this is the condition when f is 1-1. So let us see the proof. So we need to consider, suppose necessary condition. Suppose here, if we are considering that, suppose kernel of f is only one element, that is 0. Okay, then we need to prove that f is 1-1. Okay. And you know that to prove that f is 1, 1, we need to prove that if images are same for two elements, then that those elements are also going to be same. Okay, that is pre-images also going to be same. Okay, so for this, let us consider A and B belongs to R1, that is a ring. Okay, and f of A equals to f of B. Then we need to prove that A equals to B. Okay. So this implies that FA minus FB, and because FA and FB are elements of R2, so this should be equals to 0, and this 0 should belongs to R dash. Okay, sorry, R2, not R dash. Okay. So this implies that because FA minus FB in the left hand side we have, so and F is a homomorphism, so we can very much write this f of A minus B equals to 0, and this 0 belongs to R2. And you know, in the last lecture we we discussed okay, or like this we can say that if this implies that A minus B belongs to kernel of, okay, kernel of F, is to belongs to kernel of F, and this kernel of F is nothing but this has only one element, that is 0, singleton 0. So this means that A minus B has to be 0, and this implies that A equals to B. So this means that F is 1, 1. Okay. Now conversely, suppose F is 1 to 1, 1 to 1. Then we need to prove that kernel of F is identically 0. Fine. Okay, so let us take X belongs to kernel of F. Then by definition of kernel of F, Fx should be 0, and 0 belongs to R2. Fine. And this we can write Fx, and we know that under homomorphism, hello, hello. So as F is a homomorphism, as F0 equals to 0, F0 equals to 0. So this implies that x equals to 0, as we have assumed that f is 1 to 1. Okay. So uh, this means that whenever we are taking any element x in a kernel of f, this means that x has to be 0. So this implies that kernel of f is equals to singleton 0, like this. All right. So now let us see the next result. This is a very interesting that any homomorphism of a field. So far we are talking about homomorphism on a ring. Now let us see if we take a homomorphism, or if we define a homomorphism on a field, then what is the possibility of the image element. Okay. So next theorem. Prove that any homomorphism of a field is either an isomorphism or takes each element into 0. Okay. So this is a special quality of a field homomorphism on a field. Okay. Either if you are taking any homomorphism on a field, either it is going to become an isomorphism. It means that we need not to verify it is 1 1, it is 1 1. Okay. We need not to verify. Or else, if it is not an isomorphism, then it will take each element into 0. That is, this is going to be many to 1. Fine. Okay. So either it is 1 to 1 or many to 1 in this case. So let us see the proof. Of course, this is a very trivial kind of thing. Okay. We can take let f be a field and consider and f from f to r. We are taking r as ring. Okay, this is a ring. Ring is a homomorphism. Is a homomorphism. Okay. Then, of course, we have seen that kernel of f is an ideal. Okay. Then kernel of f. Just now we have seen in today this one, the first theorem here, that f is a homomorphism from R1 to R2. Then kernel of f is a two-sided ideal. That is, this is going to be an ideal. Okay. So f is also being a field. This is also going to be a ring. So kernel of f is an ideal. Ideal of f. That's what we know, or we can conclude from there. Okay. And you know that since a field can have only two ideals, okay, and since only ideals, ideal of a field are, what are they? This we have seen that in case of a field, there are only two possibilities for ideal. Either it is singleton 0 or it is f. Okay. Field f are either this is going to be 0 or f. So there are only two ideals, in fact. Okay. There are only two ideals, singleton 0 and f. Fine. So this means that kernel of f, because this is an ideal, so either it is going to be this, or in other case, kernel of f is going to be identically f. Okay. So in these two cases, the case first, if kernel of f is identically 0, okay, kernel of f is identically 0, then by the previous result, okay, then f is 1 to 1 by the last result we have seen. And then second one, if kernel of f is going to be capital F, then what you can say? Then if kernel of f is going to be capital F, then for x belongs to kernel of f, then x belongs to kernel of f, okay, fx equals to 0 for all x, okay, fine, okay, and this x belongs to kernel of f, it means what? It also belongs to capital F, okay. So this means that f takes each element of f to 0. So this completes the proof. Okay. Next theorem. Of course, this is going to be proof of a theorem in your textbook. Okay, some of the part you can get from here, and they are very easy. So I will just write it down. You can verify them. Let f from a ring R1 to R2 be a ring homomorphism. Then in that and also we can okay. Then first fr, that is fr1, that is image of the ring R1, is a subring of R2. Okay, fr1 is going to be a subring, that is this image is going to be a subring of R2. All right. Then second part, this says that if R is commutative, R1 is commutative, then fr1 is also commutative. C part, if one belongs to R1, that is identity, R has identity, then f of 1 is the identity of the subring R2. Okay, and here it is understood that the one belongs to R1 means the one is identity element. Fine. One more part we can see. The part D is that if A is an ideal of R1, then f of A is an ideal of f of R1. All right. F of R1 is subring, you know. Okay, and that is यूनिटी जो है यूनिटी पे मैप हो रहा है होमोमॉर्फिज्म के अंडर में, आइडियल पे मैप हो रहा है. ओके, इमेज ऑफ ए कम्यूटेटिव रिंग इज अनदर कम्यूटेटिव रिंग, ये भी हो रहा है. ठीक है, तो ये सारी चीजें आप यहाँ पे देख पा रहे हैं. ठीक है, यही नहीं और भी सारे इसमें आप देख सकते हैं. Next result, all these you can verify easily. Okay, there is if you get any difficulty, you can send message to me or you can ask. Okay, so next theorem, it says that let f from R1 to R2 be a onto ring homomorphism, onto ring homomorphism. Here it should be, this should be noted. Okay, onto ring homomorphism. Okay, then if R is an integral domain, then R, that is R1 is an integral domain, then R2 is also an integral domain. आप इस चीज को ऐसे भी कर सकते हैं कि अगर यहाँ पे मतलब कोई इंटीग्रल डोमेन है तो इंटीग्रल डोमेन मैप्ड onto इंटीग्रल डोमेन, दैट्स ऑल. You can say like this, okay? Integral domain mapped onto integral domain. Okay, fine. और अगर ये onto नहीं होता है, अगर onto नहीं होता है, if it is not onto, okay, if not onto and R1 is an integral domain, then f of R1 is going to be an integral domain. तब हम इसको इस तरीके से कहेंगे, फिर R2 की जगह f of R1 आ जाएगा. Fine. Part B, let us see. If R1 is a field, then R2 is also a field, okay. So in case if it is not onto, okay, if not onto and R1 is a field, then f of R1 is a field. Fine. So field पे जा रहा है, इंटीग्रल डोमेन पे जा रहा है, इस तरीके से करके हम देख रहे हैं. आइडियल पे जा रहा है. So this is very interesting to see. So in order to prove that R is a field, then R dash is a field. Do you want proof of this or what? Okay, let us see the proof of first one. That is okay. Let us see the proof. Proof of part A. It is given that R1 is an integral domain. Okay, so let us assume that and we need to prove that R2 is also an integral domain. Okay, so we need to consider that and of course one more thing we can have here that f is given to be an onto map. Okay, so we can consider that A dash and B dash they are member of R2. Okay, and then because f is onto, then because f is onto, so there exists a B belongs to R1 such that f of A belongs to A dash and f of B f of A equals to A dash, f of B equals to B dash, like this. All right. Now consider A dash, B dash, the product of these two equals to 0. Fine. Then we need to prove that either one of them, because we need to prove that R2 is an integral domain. So it means that when product of any two elements is 0, it means that at least one of them is going to be 0. Okay, that I mean to say that it has no zero divisor. Okay, so this implies that f of A dash and B dash, this we can write f of A, f of B. Okay, and this we can write f of AB. Fine, f of AB, and of course this is a 0. All right, and because f is a homomorphism, so 0 is nothing but f of 0. Okay, So this is equals to f of AB, like this. Okay. Hello. Hello. And then now, I meant to say that because 0 mapped onto 0, 0 mapped onto 0, and also one more thing. I think I have written here homomorphism or isomorphism. Here I should write, I think, onto ring isomorphism. It should be. This is isomorphism. Isomorphism. Please note it down. This is isomorphism. Okay. Otherwise, we can add a one to one also. This means that 0 equals to A times B, as F is an isomorphism. Okay. Is an isomorphism. Fine. Last two theorems were what we have written here. They are correct. Okay, ring homomorphism is sufficient for this. Okay, but in order to map integral domain to an integral domain and field to field, f need to be an onto, or at most what I see that what I can say that this should be an isomorphism. Okay, so here, okay, is A times B equals to 0, and because that A and B belongs to R1, so and R1 is an integral domain. So therefore, either A equals to 0 or B equals to 0, like this. Okay, either. Why? Because R1 is an integral domain. So this means that A equals to f of A equals to f of 0, or f of B equals to f of 0. And this means f of A is nothing but A dash and f0 is 0. So R A dash is 0 or B dash is 0. So at least one of them has to be 0. So this implies that R2 is an integral domain. Fine. So in order to prove that that if f is an isomorphism, then we need to prove that if R1 is a field, then R2 is also going to be a field. Or in other words, we can say that if R1 is a field, then f of R1 is also going to be a field. So field requires so many things, as we know. It requires that each non-zero element should be unit, and of course it should have identity. Okay, so these are the things. These are the things we need to take care. Okay, so here f from R1 to R2 is an onto isomorphism. Okay, isomorphism, as we know. Okay, since R is a field, you know that if R1 is a field, so it must have a unity, and also it should be commutative. Okay, and since R1 is a field, so 1, that is identity, should belongs to R1 and is commutative. Okay, commutative, and is commutative. So this property we should recall. Okay, fine. So what we need to prove? We need to prove that every non-zero element, okay, R2 is a ring. That is all right. So what we need to prove that it should have unity also. Okay, so since 1 belongs to R1, so f of 1, today, in fact, we have seen that if 1 is unity belongs to R1, then f R1 is the identity of R2, okay, of FR1, okay, or f of FR1, because this is on 2, so we can very much write R2 equals to FR1. So R2 has identity. So this is what we got, okay, this is what we got. And R2 is a ring, and also this, okay. And also, you know, just now, I think here somewhere I have written that if R1 is commutative, you can see here R1 is commutative, then f of R1 is also going to be commutative. Fine. And also, as R1 is commutative, okay, f of R1 is also commutative. F of R1 also commutative. So what else we need? Of course, the distribution R2 is a ring, so distribution of multiplication over addition will be there already. So we need to prove that every non-zero element should have inverse, multiplicative inverse. So for that, let us consider that A is non-zero, a dash is non-zero element of R2. Okay, non-zero element of R2. Okay, and since this is onto, so there exists A belongs to R1 such that f of A belongs to f of A is equals to A dash. F of A equals to A dash. Okay, and as you know that f is 1 to 1, so A cannot be 0. Okay, because under homomorphism, 0 map to 0. So and because f is 1, 1, so A dash, because A dash is not non-zero, so A cannot be 0. All right, fine. And because A is non-zero and R1 is a field, okay, and R1 is a field, so every non-zero element has a multiplicative inverse, has the multiplicative inverse in R1 itself. Okay, so here we have A inverse such that A inverse belongs to R1. So this implies that A inverse belongs equals to unity. Okay, and now the rest will come from here only. So we can write f A inverse equals to f of 1. And you know that f of 1 is going to be the identity of R2. Okay, this is the identity of R2. So in the left side, we can write f of A and f of A inverse equals to f of 1. Fine. All right. Fine. Hello. Okay, let us see then. So f of A, we can write A dash. F of A inverse equals to f of 1. Fine. And also A inverse A equals to 1. This would imply that f of A in a similar way, A inverse of A dash equals to f of 1. Fine. So this is 1, this is 2. From 1 and 2, 1 and 2 together would imply that this implies that inverse of A dash is equals to f of A inverse, and f of A inverse is an element of R2. So every non-zero element has a multiplicative inverse. So this means that R2 is also a field. So image of a field is also a field. That's all. That's what I wanted to tell. There is another interesting result. In fact, this will be in your exercise problem also. That prove that the only homomorphism from Z to Z, that is set of integer to set of integer, okay, are the identity and zero mappings. Zero mapping. Of course, you know that zero mapping is itself is a trivial homomorphism. All right. The solution of this it means I meant to say that you need to prove that the zero mapping identity they are homomorphism. Of course, you can very much prove this. Okay. If you write fx, that is fa map, or like just write like this. Let f from z to z, okay, be a homomorphism. Okay. So if fx equals to 0, that is zero mapping. Okay. Then obviously that f is a homomorphism. Okay. Suppose f is not is a non-zero. Okay, non-zero mapping. Suppose f be a non-zero homomorphism. Okay, homomorphism, that is, I will to say that fx is not equals to 0. Okay, fx is not identically equals to 0. That is, it is not identically 0. Thing is that, okay, for each x. So in that case, then we can very much write f of 1 and the square of this, we can write f of 1 and f of 1. Okay, because you know that one belongs to the set of integers, unity element. Okay, unity. So this means that f of 1 is a non-zero idempotent element of Z. Okay, and you know that since only idempotent, non-zero idempotent, only non-zero idempotent element of Z is 1. Okay, दो नॉन जीरो, दो आइडेम्पोटेंट एलिमेंट्स होते हैं इंटीजर्स में, एक तो 1 एक तो 0. ओके, बिकॉज वो 0 नहीं है तो इसलिए दिस हैज टू बी 1. सो दिस मींस दैट f of 1 हैज टू बी 1. ओके, अभी भी हमने देखा था कि आइडेंटिटी जो होता है वो दूसरे की आइडेंटिटी पे मैप हो जाता है. ठीक है ना? ओके, सो नाउ for any integer n, okay, n is greater than 0, we can write f of n, this equals to f of 1 plus 1 plus 1 plus 1. Okay, n copies. And then we can write f of 1 because f is a homomorphism plus f of 1 n times. Okay, n times we can write. And because f of 1 is 1, f of 1 is 1, so we can write 1 plus 1 plus 1 plus dot 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 plus 1. So here we are getting n here. Okay, so this is the case when n is greater than 0. So in case f is less than 0, in case n is less than 0, so we can write m equals to minus of n. Okay, and then in that case m is greater than 0. Fine. So in that case f of n, this equals to f of minus m, and this is equals to f of minus times of f of m, because f is a homomorphism that we have seen earlier. And by previous argument, we will be getting here negative m. Okay, negative m. So this implies that what f of n equals to n if n is less than 0. Okay. Of course, you can write here, minus times of m is nothing but n. Okay. And also, you know that f of 0 equals to 0. Okay. So so this implies that f of, if you are taking any k, then this is equals to k. This is equals to k for all k belongs to set of integers, whether it is positive, whether it is negative, whether it is 0. And this maps is what? This is identity map. Identity map. So only homomorphism, okay, on the set of integer are either it is identity or identically 0. Okay. So with this, let us conclude the discussion for today.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.